I am Jonas Seng from the AI and ML group at TU Darmstadt, and I'm going to present a joint work with Fabian Kalter, Zhongjie, Fabrizio Ventola, and Kristian Kersting, titled Bi-Level One-Shot Architecture Search for Probabilistic Time Series Forecasting. Time series forecasting is crucial in many domains. For example, medicine, finance, or climate sciences. The goal of time series forecasting is to predict future time series values based on previous observations. And recently, neural models evolved as a very accurate but often overconfident time series forecasting model. At the same time, probabilistic models uh, have also been developed, which are more calibrated, but usually not as accurate as neural networks. And also, oftentimes, they are hard to scale. So recently, predictive whittle networks have been proposed in order to combine the best of both worlds. They are a hybrid architecture that provides a calibrated uncertainty estimate, which is leveraged in order to improve the predictive accuracy of a neural forecaster component. However, in these hybrid architectures, several choices and decisions have to be made. In particular, the macro and micro architecture has to be designed. This is a non-trivial task. For example, if we decide to use a spectral recurrent neural network as a neural forecaster module, we also have to find a proper design of that SRNN module in order to obtain well working and well generalizing models. So these choices are interdependent. The design choices obviously influence the overall performance of the model, but also design choices influence each other. So this requires a lot of skill and human effort so far, and we'd like to efficiently optimize both the macro and micro architecture jointly and automatically in order to obtain good and well-performing PWN architectures. Since PWNs are a crucial part of that work, let me briefly explain how they work. So given the time series, we start by passing it through a short time Fourier transform that yields a spectral representation of that time series in the spectral domain. This representation is then fed into a neural forecaster module and a Whittle probabilistic circuit. The neural forecaster provides a prediction of the next value of the time series, while the Whittle PC provides a likelihood over these values. Then we obtain forecasting loss and, as said, the Whittle likelihood, and combine these two into the Whittle forecasting loss. The Whittle forecasting loss aims to weight down outlier data points using the predicted Whittle likelihood, while the forecasting loss is a usual forecasting loss, for instance, MSE. That way, one aims to find well generalizing models. Our approach aims to design this hybrid architecture I just proposed, and therefore we designed a hierarchical search space, which consists of a macro search space and a micro search space. In the macro search space, we have to decide for a module type, for example, choosing a spectral recurrent neural network or a spectral transformer, while the micro level corresponds to really designing these modules then. So designing the cell architecture of the SRNN or the exact architecture of the transformer then. Our algorithm operates as follows. First, we start by passing an input from the training set through the macro and micro level. This is done by computing a weighted sum of operation outputs Then we obtain the training loss and apply gradient descent in order to update the modal weights, which are not the architectural weights. Those are the modal weights. Then we proceed with choosing a random X from the validation set, again passing it through the macro and micro architecture using the same weighting scheme, and then computing the validation loss of that output. And then we apply gradient descent in order to optimize the architectural weights. To evaluate our method, we compare the architectures found by our algorithm with several handcrafted baselines, which are the temporal fusion transformer, deep AR, ETS, which is a simple statistical baseline, and PWNs. Further, we considered 10 challenging datasets, starting with the M4 competition consisting of 6 subsets over multiple domains and timescales. The power dataset, which is a record of power consumption over time. Exchange dataset, which records historic currency exchange rates. The wiki dataset that reports daily hits of Wikipedia pages. And the solar dataset, a record of local solar energy production over time. In our empirical results, we find that our method identifies state-of-the-art architectures, often outperforming all baselines. And compared to all possible PW and macro architectures, we always outperform those baselines, except for exchange. Also compared to non-PWN baselines, so TFT, ETS, and Deep AR, we outperform those in 7 of 10 cases, which shows that our method effectively optimizes the macro and micro architecture of PWNs. Also, looking at architecture statistics, we find that our method, just like human experts, tailors the architectures to the dataset at hand. So for example, looking at M4 quarterly and M4 monthly, we find that for M4 quarterly, different operations are selected than for M4 monthly. This is because M4 quarterly and M4 monthly have some differences in the data characteristic, and we see similar results for exchange and wiki and solar. To conclude, our bi-level one-shot neural architecture search leverages uncertainty estimates to foster the identification of well-generalizing architectures. So this is the Whittle forecasting loss component here that weights down outlier data points. And also we find that the bi-level one-shot NAS approach finds good hybrid architectures outperforming handcrafted state-of-the-art models for time series forecasting.